In this particular class, you'll be learning what the curved surface area of a cone is, the total surface area of a cone, as well as the volume of a cone. So if you've struggled understanding or memorizing these formulas, then this particular video is for you. Considering this cone that we have here, now let's think about the shapes that came together to form this particular cone. So if you think about it, many people will say a cone is formed from a triangle and a circle. They're actually wrong. A cone is formed from a sector and a circle. So let's look at it this way. If I have a cone and I have a sector, now this is the shape of a sector. A shaped sector is this way. So I believe some of us have taken pizza before, and then when we take out a slice of pizza, you notice that it has exactly this shape, and that's a sector. So this is the minor sector. Then the remaining size, the remaining pizza that you have when you take out the slice, that's known as the major sector. So we have a cone is made up of a sector, a shape like this, and a circle, right? So if I fold this, so you notice that it looks exactly like a cone, like a cone for ice cream. So if I fold this, then cover the bottom with a circle, then I have this cone that I have on the board. So a cone, a solid cone, is made up of what? A sector and a circle. So we have sector plus circle will form a cone. Now, the main reason why we need to know that first is because the understanding of the shapes that came together to form this cone will make us understand how to find the curved surface area and how to find the total surface area. Now, let's go to that quickly. So, when we talk about the curved surface area of a cone, we are basically talking about the sector, only the sector. Now, when we now talk about the total surface area of a cone, we are talking about both the sector, the area of the sector, and the area of the circle. Now, we need to find what the area of the sector is. Maybe we can find the curved surface area of a cone. And after we are done with that, we go into finding the total surface area by adding the area of a circle. So, how do we achieve that? So, we have a sector. Let's assume this is our sector. We have this sector here, and then let's here be, of course, this is the radius, because if I cut out a circle and I have a sector this way, I have a sector. Any line drawn from the center of the circle to any part of the circumference is my radius. So if I bring it out, automatically here is still my radius. Then this will be the angle theta of the sector. Now, my goal is that if I can know the area of this sector, then I know the curved surface area of a cone, because when we talk about the curved surface area of a cone, we are basically talking about the area of this sector. So what is the area of a sector? Generally, the area of a sector is given by theta over 360 times pi r square. Theta over 360 times pi r square. Now, I want to derive this for the formula for the curved surface area. But before I go into that, if I consider this sector shape that I have here, and I fold it into a cone, that is, what I have here is this sector that I have here. I have angle theta, then I have here is my radius. If I fold this to form a cone, you remember that it's going to give me something like this. Then automatically, this side of the sector is the same as this side of the cone. Now remember and recall that for a cone, this side is known as the slant height, while the middle line here is known as the height. So that means that I can say that the radius of a sector is the same as the slant height of a cone. So that means in this formula for area of a sector, then I'm going to have that the radius, that is the radius of the sector, is the same as the slant height of the cone. So we would have that theta over 360 times pi L square. Now, before we proceed, there's another thing that we need to note. So let's consider something different. If you look at this, there's something called length of an arc. If I take out the cone this way and I have this is still my radius, right? So, and the distance from here to here is called an arc. It's like saying from point A to point B is like along a circumference. So here is the length of an arc. So we could consider the length of an arc and compare it with the area of a sector to see what we are going to derive. So let's consider the length of an arc. So having that, the length of an arc is given by theta over 360 times 2 pi r. That's the length of an arc. Theta over 360 times 2 pi r. So that means that if we have that sector, the distance from here to here is the length of the arc, and this radius, this is our radius. Remember, radius of the sector, then we still have angle theta here. So this is the length of an arc. So the length of an arc is given by theta over 360 times 2 pi r. Now, if you remember what we did here, where here became L square, we can do the same thing to this, because if we turn this to a cone back, this radius of this sector that we have here will be the same thing as the slant height that I said earlier. So that slant height, because if you compare the sector and the cone, this radius of the sector here was theta is the same thing as slant height of the cone. Very important. So that means that for the length of an arc, I will have theta over 360 times 2 pi L. So let's consider what we have now. So we have these two terms, these two formulas that we have here. So let's compare them together. So we've successfully shown that the area of a sector can also be written as theta over 360 times pi L square. That has been settled. And as well, we showed that the length of an arc is theta over 360 times 2 pi L, because this L is the radius of the sector, and it can also be known as the slant height. Same thing for this, radius of the sector can also be known as slant height. But if I consider this length of an arc formula, I have L equals to theta over 360 times 2 pi L. If I try to make theta over 360 the subject, what I will have is I will divide both sides by 2 pi L, then this cancels this. Then what we are going to have left is length of an arc, because this is the slant height. Length of an arc is different from slant height. So length of an arc over 2 pi L, because that's what we have here, 2 pi L, is equals to the last thing that we have here, theta over 360. Now, we did that because we want to manipulate our way to making sure that this theta over 360, we represent it with L over 2 pi L. So this is the length of the arc, and this is slant height, so they cannot cut. So what I would have from there is, if I consider a sector again, let's look at a sector. This is a sector, this is length of an arc. Remember, this is slant height, small l. So when we consider the length of an arc, the length of an arc is a part of a circumference. I said that before, a part of a circumference, because this is a circle. So from here to here is an arc. So, and this is also a circumference. This is also a circumference. So that means this length of an arc, L, can be rewritten or represented with the circumference of a circle. So therefore, we have that this can be written. So we have theta over 360 equals to L. This L becomes the circumference of a circle, 2 pi r. Then we have 2 pi r over 2 pi L. So from here, 2 pi cancels 2 pi. Then we can agree that theta over 360 equals to r over L. Now we are getting to the last part. Now, from here, since we know that theta over 360 equals to r over L, then let's put it inside this area of a sector, because we know already before that the area of sector is curved surface area. So our goal is just to find what the area of sector is. So what we did was we tried to make sure that theta over 360 could be represented with R over L. That was our goal. We've already shown that theta over 360 equals to R over L. So what we do next is that in this formula that we know that that's the curved surface area formula, so we could say area, which is also the curved surface area of a cone, will give us, instead of me writing theta over 360, I would write R over L times pi L squared. So of course this is slant height, this is slant height. So we could say L deduct this, that is when they cut, what do we have left? We have pi, we have R, we have L. So from here we could say that the curved surface area of a cone, the curved surface area of a cone is equals to pi R L. So you need not to prove all of this in the exam hall for you to remember it, but it's quite important for you to note some specific things that I said, and that is when you know that the radius of a sector is the same as the slant height of a cone, which is very, very important. So the curved surface area of a cone equals to pi R L. Like I said earlier, the total surface area of the cone will involve the circle and the sector. So the total surface area of this particular cone will be equals to the sum of the area of this sector and the sum of the area of the circle. So we said the area of this sector is known as the curved surface area, and we just proved it that it is pi RL. Then the area of this particular circle is what? Pi R squared. So this that I have here is the total surface area of a cone. So we need to find the volume of a cone. Let's quickly get right into that. I need us to note something very, very important when it comes to cone. Now, when we talk about the capacity of a cone, I mean the volume. Cone is part of the family of shape of pyramid. So what I mean by that is pyramid and cone, they have the same formula for volume. So the formula for the volume of a cone is given by 1 over 3 base area of the cone and the height multiplied by what? Base area of the cone and the height. So what that means is that we are going to have 1 over 3 times the area of the base of a cone is a circle. So the area of a circle is pi R squared and our height is what? H. So therefore we have that the volume of a cone will give us 1 over 3 pi R squared H. That basically implies that the volume of a pyramid is also 1 over 3 pi R squared H, because they are in the same family of shape.